Good afternoon, everyone. It's a great privilege to be here and to share with you this exciting project. When people ask my two boys, what does your dad do? They say he develops and plays computer games the whole day. And then when they go, that's really cool, and they follow it up with, and then he gives them advice how to get high scores. So this is kind of what we do. It's quite accurate. We work with organizations around the world, both private and public sector, to help them figure out why they are not achieving their high scores. Why are they not achieving their performance targets? How do the organizations or departments or supply chains they work in actually work? Figuring out how the game really works, and then to give some advice in terms of what is it that they can do, what changes they can make in a way that they plan or execute or continuously improve their organizations that will allow them to achieve the highest possible scores. Frequently, it's about what is the highest score that you can achieve with the current level of capacity, capability, etc. So the start of this project really happened when we were asked by one of the largest resource companies in the world to develop a computer simulation game for all their supply chains. They wanted their supply chain managers and executives to be able to play a game to understand why their past efforts of implementing theory of constraints, which is one of the areas that we work in, have not achieved the performance that they expected. And what we found was that they make common mistakes that many organizations make. They confuse theory of constraints with debottlenecking. Debottlenecking has the impact of balancing capacities over time. And when you have a system with balanced capacities, as you probably know, you get a chaotic system. And a chaotic system, the performance that you get out of a chaotic system is substantially lower than the capability of its bottleneck and will vary dramatically over time. It's completely difficult to predict. The second mistake that they make is they implement a set of new rules. They implement theory of constraints, for example, but they keep on pushing to forecasts rather than pulling based on actual consumption. And the assumption is always that, yes, we like the idea of pulling based on actual consumption, but it's far too costly. So we developed this computer simulation game. They really enjoyed it. And one of the managers came to me afterwards and said, we have this new supply chain. You helped us understand what's the best performance we can achieve with current capabilities across all of our supply chains, but we have this unique opportunity of designing a complete new supply chain. It doesn't often happen that you are building a new mine and have the ability to impact the capabilities that need to go into that supply chain to achieve the highest level of performance. So the project overview is we worked with they're one of the largest resource companies in the world. They're over $80 billion US. The project scope related to the design of a potash mining operation and a full supply chain of the outbound logistics. So they wanted to understand, based on the current design that had been given to them by their design engineers, firstly, what is this supply chain, based on the design specifications that we've given, what is it actually capable of delivering? They wanted to enter a new market, and it was critical that they had a competitive advantage, that whatever they claimed that they could deliver at the lowest possible cost. They wanted to design the supply chain in a way that differentiated themselves from their competitors, not only in terms of reliability and speed of resupply, replenishing, but also in terms of the ability to recover from both natural disasters and man-made crisis. It's a kind of idea that Nassim Taleb introduced recently called anti-fragile. You don't just want to design systems and supply chains that are robust against volatility. You want to design organizations and supply chains that can actually benefit from volatility, and that was part of the design scope. And of course, they differentiate themselves as one of the lowest cost providers in the world that allows them to cope with downturns much longer than their competitors. So whatever solution design we came up with, it had to deliver the lowest possible cost and capital investment. The actual model, for confidentiality, we are not showing exactly where the mine is and the supply chain. So it's a kind of a representation of it. But it started with the mining operations. They wanted us to include in the model the full mining operations, including planned and unplanned maintenance. There's an actual mining operation where they extract the ore, and then there's processing plants and loading bays that load trains with two products, including a third sort of off-grade product. That product goes into mine storage. From the mine storage, then a decision has to be made on whether to ship it to an export channel via a port or to ship it towards hubs for local distribution. About 90% of the total volume that the mine produced was going to exports and about 10% to local supply. Of course, at the ports and the hubs, there are storage capacities. There's a decision about what mode of transportation should be required. Should it be trucks, barges, rail for the local side, and for the international side, the size of the ship, or should it be containerized or bulk ships, and then off into the markets. And they wanted us to be able to model also the availability and cost at the customer level itself. As you know, a push-type model just pushes the product into your customers, so you don't actually see the higher working capital on your own balance sheet. They wanted us to be able to build a model that can capture the full total working capital. So if you simply are pushing product into your customers, there should be a penalty for that. So the four questions that we had to answer, apart from the question of how much can this design that we've already come up with actually deliver in terms of ramp-up capacity to ramp up all the way from 0 to about 13, 14 million tons per year. The other questions that they asked us is, while we still have a chance, can you give us some advice on what is the best possible supply chain design? So they contracted with a very large consulting company that gave them all the options, how many ports, which ports can be used, how many hubs, what hubs can be used. So I wanted to find out what's the optimum design. Is it multiple ports, multiple hubs to protect yourself against risk, or is it a single port, single hub, and if so, where should it be located, on the East Coast, West Coast, South Coast, etc. The next part was, once we've chosen that design, how much storage capacity is actually required at the mine, at the hub, at the ports, and even at our customers. The third question was how many rail cars. They had an option of buying custom rail cars or designing their own rail cars. The benefit of the standard rail cars, much lower capital investment. The benefit of custom design rail cars is much faster loading and offloading rates. So was it worthwhile to pay the extra money to develop custom rail cars? And then the last part was they threw it in based on the previous simulation work that we had done that showed a clear benefit in most conditions of applying a pull strategy towards managing your supply chain. They said, does it actually make a difference? We're only doing 2 products, maybe 3 products. Does it actually make a difference whether we are pushing based on forecast into the supply chain or whether we are pulling based on actual consumption or some kind of hybrid in between? They thought that might be just interesting. They didn't think that in terms of consequential damages that it would make a lot of difference. It's a very large supply chain, so they thought that getting question 1 wrong might be a few $100 million of profit over a 20-year period, whereas getting question 4 wrong might be tens of millions of dollars. So I'll hand over now to my co-presenter, Andrey, to share with you, first of all, why AnyLogic was selected and show you a demonstration of how the model actually works to answer those 4 questions.
Thank you very much, Alan, and good afternoon. I'm going to talk about why have we chosen AnyLogic for our project. It actually allowed us to design a flexible, fully self-configurable model of the supply chain, and that satisfies the key requirements that we had before we entered this project. Before we entered this project, the customer has already had the simulation built for them by some other company, and it has they were able to get some benefits and advice from it. But the main shortcoming of that model was, in many respects, it behaved like a black box. It just gave them the numbers, and without any explanations why the numbers are that, but not these, and what's actually happening in supply chain. So we had very high expectations from our clients' team in terms of the transparency of all the results of the simulation. We also had, of course, to include many sources of randomness because we modeled port strikes, weather delays, and the impact of the weather delays to the rail transportation, all the ports operations, which are also subject to some disruptions. We modeled also disruptions at production side, and of course, the main source of randomness at our model was the variability of customer demand. As I said, we were asked to build the simulation in a way that most of the interdependencies and most of the numbers could be easily explainable out of the model presentation, and if not, at least out of the Excel report that was built at the end of the simulation. Of course, model considered many financial implications and calculated financial performance metrics such as cost per ton, etc. I will now go to the live demo of the model. That's the setup page of the model. So we were asked to make it as configurable as possible. So all the model is fully configured from the Excel file. So the scenario now is loaded to here. But on top of that, in the user interface, all users can set up all the parameters, virtually all the parameters, without having to jump back to Excel file and modify the data there. We have all the ramp-up parameters here, all the schedules, all the variability parameters, etc. We also have this stock management parameters. We choose the policy, which policy to apply to this scenario. In this case, it's pool policy. Alan will be speaking about these policies later on. Okay, and we can start the simulation and see the things running across. So what we can see here is the mine starts producing the product and supplies all the customers all over, both domestic and export customers. And all the plots are can be there are a lot of plots that are shown at the same time. And for our team, it was very, very important so that everything that's happening in supply chain is easily observed and explained. And from the technical perspective, we have a lot of abilities of zooming in into the plots, all the plots. So you can see that we have the automatic algorithm of adjusting the target stock levels, and it's working when it sees that when it feels that the target stock level should be decreased at decreases then, etc. We can even look inside some seaports. So all the seaports, mines, and customers are active objects with possibility to look inside them and see what's happening inside the port. In this case, we can see here the trains coming and offloading the product to the storage, and big sea vessels coming and waiting in the open sea, open ocean, and shuttle vessels taking the ore, taking the product from the storage to the sea vessels. And of course, we have all the statistics and all the logs here at the screen, and all of this are recorded and dumped into the final Excel report. So we can also, for example, have a look inside the mine. We have some issues. That's because of the resolution of the screen, but nevertheless, we have this plots, for example, representing tons waiting for loading, etc. If I switch back to presentation, I want to talk about two capabilities that we also had in our model. The first one is scenario comparison. It is there to simplify the scenario analysis for both us and our client's team. The model we have given this model to our client's team, and they continue to get some benefits from that. So on the columns, you can see here that we tested different stock management policies and all the financial and operational results that we have. So it shows at a single screen. It shows all the financial and operational result that we have with this and that policy, stock management policy. Another capability that we've built into the model is the sensitivity analysis. In this simple case, you can see there's some screenshot of analysis of how sensitive all the supply chain performance metrics are to storage capacity in a port, storage capacity in port, and number of rail cars. This also to a great extent speeded up the scenario analysis and allowed us to get the benefit from the simulation as fast as it was possible. And I will now hand back over to Alan to speak about the business implications of the project.
Thank you. So the graph that you're looking at the moment is one of the outputs that we got directly from the model. As Andrey mentioned, we didn't only want to be able to run the model as a single experiment, but we wanted to run the model and do sensitivity analysis. In this case, we wanted to see for these 3 different modes of operation, push, hybrid, and pull, how does the service level change as on the horizontal axis, I'm adding additional rail cars into the system. So starting from about 2,500 rail cars all the way up to 5,500 rail cars. How does it actually increase the service level? And then vertically downwards, second dimension is as I'm changing the amount of storage capacity at the port and the mine. This is in 150,000 tons of storage capacity all the way to 500,000 tons of storage capacity. And as you can see, world-class performance was defined by them as service levels above 98%. And we couldn't find one scenario where push gave us anything close to 98% service levels. We could find it with hybrid. The first time it came up was around 4,500 rail cars with 350,000 tons of storage capacity. But pull was already achieving that level of performance at a combination of either 4,500 and 250,000 or 3,500 rail cars with 300,000 kilotons. And this was really surprising to them. They didn't expect that the system was so sensitive in terms of the storage capacities, and it was in fact lower than what their original design was. Just as a brief overview about why is this taking place, and we used the model to really understand why will push keep on giving you poor service levels regardless of how much capacity you throw at it. And basically what happens is when you have a single product, it doesn't matter when you are sending product down the supply chain, because people don't have a choice. You don't have to make a choice about what to send to export to inland, what to send from the hub to onwards. As soon as you're adding 2 or more products, those products occupy capacity, they occupy storage. When you are pushing, whatever capacity or storage you've added will just be automatically filled up. And then you very quickly get into a blockage situation where your storage capacity is filled up with a long product. Downstream customers are demanding another product, and you simply don't have the capacity or the storage to put that product down. So it was really interesting to see why push was, in all cases, much, much worse than pull. Some of the clever algorithms that we included in pull, for example, one that Andrey showed was not just deciding on the storage capacity or the target stock level and keeping that constant, is actually then dynamically deciding based on whether you've got too much red, your stock's frequently going into the red, when to increase your target stock levels, or if you have too much green, your stock on hand not coming out of the green zone, the top part, which means that you clearly have enough, you can safely reduce it without paying the cost. But even down to the mine, should the mine be running very long batches to minimize setups, or should they dynamically change the batch sizes based on what's happening downstream in terms of consumption? So what we did was we built the model, and then we started adding complexity and volatility or randomness to the model. And what we wanted to see is how does the service level get affected when you are adding complexity and volatility to the model. And what you can see is push is dramatically negatively impacted by any levels of complexity or variability. Complexity in terms of adding additional products, adding additional customers, adding additional hubs and ports. Whereas with pull, you are maintaining an exceptionally high levels of service levels, regardless of the complexity and volatility that you're adding. The next obvious question comes up to say, but at what cost? Surely running a pull supply chain must be much more costly to maintain this level of service, regardless of the volatility. So, of course, we generated this graph that showed the cost per ton impact of push versus hybrid versus pull. And what you can see is push is always the highest cost per ton. They were following push because they thought it was the lowest cost per ton, simply because it was trying to maximize the utilization of the mine, which in this case wasn't actually the constraint of the supply chain. It showed that with pull, yes, pull does, the cost per ton does increase over time as you're adding volatility and complexity, but it always maintains a substantial advantage over any other strategy. So in summary, in terms of what have we found, we were able to generate this directly from the model in terms of the scenario comparison to show you in red the worst performer, in green the best performer, and to show them the difference of going back to those 4 questions. If you made a really bad decision on the supply chain design, what's the consequences of that? How much did it cost you? If you made a really bad decision on storage capacities, how much did it cost you? If you really made a bad decision, the difference between the best and the worst, on number of rail cars, how much did it cost you? And finally, in terms of push, hybrid, and pull. Some elements to highlight: delta cost per ton sold, the difference between the best and the worst, what our model recommended versus what they decided to do, were initially, based on this analysis from the previous simulation model, was $3 a ton. At 13 million tons per annum, that's $39 million of net profit gone, simply because you've made a bad choice in terms of whether to push or pull. And that's just with 2 products. If you're going down in terms of the actual total tons produced, you are looking at 4.1 million tons difference between push and pull with exactly the same capacities, same volatility. Multiply that by $300 per ton, that's $1.2 billion of revenue gone simply because you made a bad choice regarding of which policy to use. So overall, once this analysis was presented to the top executive, it really was a very simple decision. There were no doubt anymore in the room about which policy to follow. And we could clearly show the benefit of where storage capacity, additional storage capacity will help versus harm. So in summary, pull was recommended because it maintains world-class performance, a critical aspect because they are entering a new market. They needed to differentiate themselves in terms of service levels. And it maintained that advantage across a whole range of demand and supply variability, which is in the commodity market exceptionally critical. It doesn't help to select a strategy that gives you an advantage under certain conditions and not others. It achieved this higher level of service level also at the lowest cost per ton and smaller working capital and capital investment requirements. It was much more resilient in terms of changes of volatility, but it also, we started experimenting with what rules could we use, not just to make it more robust, but to make it anti-fragile. Anti-fragile, very simply, you get more upside from a plus 20% change in demand or supply than what the downside is that you get from a minus 20%. And we were able to use the simulation to model what are the type of rules that will allow them to limit the pain during a downturn without limiting the gain during an upturn. Pull also offered their customers much lower working capital. If you're replenishing more frequently on actual demand, the level of stock that the customers need is much less. And lastly, it allowed them to maintain much lower levels of inventory at the ports and the hubs, where when you are buying storage capacity at a port, it comes at an extreme premium compared to, for example, putting storage capacity at a mine. So that was our presentation. We have some time for questions, so we'll welcome any questions that you might have.
So thank you very much for this presentation. You showed us some great examples of making optimizations before you start running the simulation, and then a good example of that push-pull versus hybrid during the simulation. It almost sounded towards the beginning of the presentation that there needs to be other decisions made to recover from situations or react to random things as they happen. If you had any kind of optimization or decision logic in the model, can you expand on that?
Sure. So in theory of constraints, one of the things that we do is we try to understand how do you help people make better, faster decisions. And there's essentially three types of decisions we make. We make planning decisions, which are decisions before we start doing the work, like what does the supply chain design look like? How do we allocate resources? How do we decide when to release work into the system? Secondly, we make execution decisions, which is decisions we make while we are doing the work. How do we prioritize when to intervene, when to work overtime, when not to work overtime, when to batch, when to multitask? And then the last part is we make decisions from an ongoing improvement. What to measure? Should we measure variances of everything, or should we pay attention to what's the main causes of things? So once we had built the model, we were able to show them and allow them to experience how they could make mistakes in one of those three areas. And in fact, we recently got an email just 2 weeks ago to say that they are now using the model to help them answer questions that they never even thought about from a design perspective. So for example, I keep on pushing down the storage capacity that's shared between products are suddenly filled up with one product. What should be the rule in terms of to make sure that that doesn't happen, and suddenly you've got trains queuing up because I can't deliver, there's no space. You've got ships queuing up because the product that they're looking for is not required. So the model has now been used to really influence directly not just the design of the overall supply chain, but the detailed design of each section of that supply chain, including the mine.
Hard code these decisions into the models, right?
No,
we are write the logic to make the decisions into the model.
As far as possible, whatever variables we are putting in, so we'll specify a rule and show you the parameters that you can either specify in the Excel input screen or via a simple user interface. So not to hard code anything inside of the model.
Thanks.
My understanding from your model is multi-year study for simulation, and you showed us that there is a cost decrease or commodity price decrease and demand decrease. And I was wondering, how could you integrate your model? How did you consider price elasticity of demand to integrate every year's output and prices? Based on higher prices, you will get less demand. And did you use system dynamics to combine this, or do you see any opportunity to use system dynamics to see this multiple year, maybe decades of planning time horizon?
Sure. So it wasn't part of the scope to change the prices based on commodity markets, and also because they are one of the players, they directly influence the prices. So if there's an oversupply of product in storage, it actually reduces the price for everyone. But the way that we've built the model now allows them to do those type of analysis and to see the consequences of their decision. For example, you get to the end of the year, there's a kind of you want to make your balance sheet look good, so you sell off all the inventory. And the question is, does this actually help? No, it's a disaster, because you start the new quarter, you don't have any inventory to sell, plus you've depressed the selling price in a whole market that dramatically reduces the profits for you and competitors. So the way that we've built the model allows them to now do those what-if analysis.
So my understanding is you change the supply part instead of demand decrease or demand increase. Is that right?
No, we modeled inside of the model fluctuations in demand and supply, but not fluctuations in selling price. So we kept the same selling price, but we modeled fluctuations in both demand and supply. But the model has been created in such a way that it's very simple for them to add in fluctuations on price, but also to show how they negatively impact the price when they are oversupplying based on push.
Can you speculate on how generalizable push versus pull policy is in other situations, or does this have to be run on every specific, case?
I think there are general concepts for push versus pull. For example, in push, we allocate resources and stock based on forecast. And what we know is the longer the time horizon of the forecast, the worst the actual outcome will be, so it's guaranteed to have shortages and surpluses, whereas pool doesn't allocate all the resources or all the stock. It waits for actual consumption and allows you to dynamically update it. So there are general concepts, and we are using the same structure of the model for many different applications, including high-tech and others that we are busy with. But the actual implications, we ask them, so how is this concept translated in your environment, for example?
Did you have general concepts about what you think theory of constraints would reveal, and then develop the simulation in order to illustrate these concepts after the fact? Or did you actually conduct a theory of constraints analysis for this particular case?
We did both. The theory of constraints, for example, has a generic rule on how to dynamically adjust buffers based on what's really happening, the too much red, too much green rule. So what we did was we used the model to show whether that rule will give better outcomes than what they're currently achieving, and if not, how do we need to modify the rule? So it's allowing us to do both to show the benefit of switching to a known, very well and documented and robust rule developed in theory of constraints, but in case it doesn't give optimum results for their specific application, how do I make a modification? So an example is we've done a big simulation project for a book publisher, and the rule that we've developed for too much red, too much green works really well until you get down to 3 books on the shelf. So if you have one book, what does red, yellow, green mean? If there's 3 books, green means you have 3 books. 2 means you're in the yellow, 1 means you're in the red. So too much green, too much red works really well to decide whether to increase or decrease. But what if you end up with just 1 book, that most of the retail books, what should now be the rule to decide whether to keep stock of that book or not to keep stock of that book? So that's what we use the model for, is to start off with a generic known rule that we know deliver great results, and then to see what are the boundary conditions where it doesn't work and how to modify that rule.
Did you include these rules within the model, the theory of constraints, general rules within the model?
Yes, we include all the parameters of that, so how frequently to check, how much to increase by, etc.
If you had not done that, would the eventual outcomes have become apparent to the user?
All the models that we build, we include the standard theory of constraints rules with all their parameters so that it's possible to tweak them to see if you can get better results.
You can switch over to the screen. Yeah. I think that's
so the screen that I'm not sure how to switch over.
you can switch over to the back to the laptop.
So, for example, here, if you selected pool here, it gave all the parameters that you could modify to change the way that, for example, the theory of constraint rule helped you decide what's the optimum batch to produce, how frequently to do setups, when to change stock levels, how much protective capacity to maintain within each of the nodes in the supply chain. So we made all of those variables.
Hi, thank you for the model. It's quite rich. You were looking at 3 things. You were looking at storage capacity, rail cars, and stock management across pull, hybrid, and push. So that's like 9 models probably. So one question is, how did you actually start building? Did you start with like a section and then expand? Start with this, one part and expand out, or just what was your building paradigm? And when you talk about the algorithm for your stock model, was it agent-based or discrete-based? And was it, if it was discrete-based, was it a block of components that you brought together for your algorithm?
Sure. So just a clarity thing on push is basically you're pushing stock into the supply chain based on your customer's forecast or your distributor's forecast or your own forecast. Pull is where you are completely basing on the actual consumption at the consumption points, deciding how much to replenish. Hybrid is essentially you are pulling from your own hubs and ports, the areas that you own. You let actual consumption dictate how much the mine is producing and what grade and product is producing, whereas the hybrid part of that is to say your customers are still placing orders on you. So that was the difference, is pull, hybrid, push. Hybrid is sort of a pull where you can, push where you have to. So I'll ask Andrey to answer the other two questions that you have in terms of technical modeling.
Yeah, thank you. Of course, it's an agent-based model. So every location and every vehicle, be it train, vessel, truck, is a separate agent, and they interact with each other. From the development perspective, we usually develop the models like this in the following manner. So we first start adding all the main objects as an active objects to the model, and we start modeling the basic behavior of all the objects. So all the parameters, so that all the parameters are used, all the things are moving, all the stock is moving from A to B, etc. And once this base logic is ready, we start to add some management algorithms like push, pull, hybrid, whatever, dispatching, train dispatching algorithms, etc. on top of that. So we now know for sure that all the mechanics is good, and all the things are shown on the presentation, all the stock plots are shown, etc. And after that, we put in this algorithms. For example, in this case, it was push, hybrid, and pull. And of course, it's kind of a lot of complexity, but when you split it up like this, it becomes easier. So you base logic first, then algorithms all over the supply chain with this base logic. The algorithms is actually written by the Java code, and it's just the AnyLogic has complete visibility of all the objects, all the active objects, and all the parameters, so I can access them by code. So once I have basic logic in place, I can apply any algorithms of any complexity that I just write by code and put it into the model.
I guess thinking about weather and when a tsunami hits a region like this, it can shut down things for 2 or 4 days or more. When time is of the essence, is your model like this useful for looking at what to turn on first, how to you react when you're working on a recovery plan?
Yeah, so as I mentioned, we wanted to really stress test the supply chain by throwing all sorts of volatility to it. But the way that the team built the model is that while the model is running, you could, for example, click on a link between the mine and the port and say, this goes down, there's some kind of snowfall, or there's a strike at the port. And I can actually dynamically see, because push and pull is running directly together, they can see which of these two rules would respond best to that. So we built the model in a way that you could pre-program all the events that you wanted to model, but you could also interact directly with the model and say, the port has just gone down, it's going to be down for 3 weeks because of a strike, what would happen? And that's kind of the next evolution that they're thinking about using the model, is rather than starting up the model and creating steady state by building up stock, why not read the actual conditions currently that you face in reality directly from your SAP system into the model, see what is the event that you need to make a decision on how to respond, and decide on alternatives and use the model to see which of those alternative reactions will give you the best outcomes. So that's part of the future scope that we are looking at. Thank you.
Thank you.